So along the center line connecting the radiating edges, it is fed. So at the point x0, y0, and LW or the patch is in the xy plane. That is what we are going to consider. The resonant resistance is almost independent upon the thickness of the patch. That is a major characteristic. But it is proportional to epsilon r, dielectric constant of the patch antenna, and it is directly controlled by the location of the feed point. Maximum is at the edge, minimum is at the center. Why maximum at edge, minimum at center? Because at the edge voltage is maximum, or E is maximum, current is minimum, therefore at edge it will be maximum. At the center voltage is 0, therefore impedance will be 0. As you know, R is equal to V by I, and so when V is equal to 0, R is equal to 0, and when V is maximum, R is maximum. At the edge it will be maximum, at the center it will be 0. So that is one point. Location depends on the feed point location, 0 at the center. Generally it is fed along the center line for y is equal to W by 2. That maintains the symmetry and minimizes the excitation of undesired modes. So we want to excite it in the dominant mode. So TM10 mode will be excited if I feed it at the center line. We had a discussion on this in the last class, taking example of waveguide. We are not going to elaborate on that. This is proportional to the square of the cavity mode field at the feed point. That is, if the field is Ez, then Rin will be proportional to Rin square. Rin will be proportional to Ez square at the point x0, y0. Now, for the dominant mode, for the 10 mode, Rin is equal to R edge cosine square pi x0 upon L. This we have already seen in the last class, so I am not going to explain how this comes or what it is. But this R edge is the impedance or the resistance at the edge. It will be between 100 to 200 or 100 to 300 ohms. So this is about a resonant resistance. Resonant resistance, what is resonant resistance? The resistance that it offers at the resonant frequency. So beyond the resonant frequency, this resistance will be different. It will not follow this rule. But exactly in the resonant frequency, this is the rule. Beyond the resonant frequency, actually this resistance or input impedance, that depends, that is a frequency dependent term. As you know from the transmission line model, Yin is equal to the expression on the right hand side contains a term tan KL, right? Or yes, since it contains the term tan KL, K is frequency dependent. Therefore, Yin is frequency dependent. So at resistance, that will become Yin will be purely real. 1 upon Yin will be Rin, which will be following this. Now let us consider the bandwidth of the patch antenna. This is another characteristics. So let us consider the bandwidth. Okay. For substrate and effects of substrate and the geometry on the bandwidth. What are the effects? This is directly proportional to substrate thickness. Why it will be directly proportional to substrate thickness? The more the thickness, the loosely attached electric fields, because as you know in the capacitor, C reduces as you increase the distance between the plate. Epsilon A upon D, as I keep on increasing D, then C will reduce. Why C reduces? Because fields are loosely attached between these two plates. So if I increase the substrate thickness, then field will be loosely attached. So therefore, if field is loosely attached, then it is easier for the field to detach from the structure and get radiated. So if it is loosely attached, it will be radiated easily. So I get more radiation over a larger frequency range, because over all frequency range it will be loosely attached. Therefore, the range of frequency will also increase, bandwidth will increase if we increase the substrate thickness. Then next is, if H is very large, so which means if we are increasing H, we are going to increase the bandwidth. Therefore, we can take infinitely thick or very thick substrate to get a very large bandwidth. That is not possible. If it is larger than 0.05 lambda 0, lambda 0 is the free space wavelength, then the probe inductance that I discussed in the last class, that will come into play. So that will become very large, and since that is large, it will be difficult to match, and you have a large inductance, therefore there will be storage. So again, everything good goes to knob. Then second part is, we have assumed that substrate is thin, so there is no variation along the thickness. So there will be higher order mode along the thickness if it is more large. So that we cannot do, that we cannot afford. Then the bandwidth again is inversely proportional to epsilon r. Right. Why it will be inversely proportional to epsilon r? If epsilon r increases, then as I told you, capacitance will increase. But epsilon r decreases, capacitance will decrease. Sorry, epsilon r decreases, capacitance will decrease. Right. So it is inversely proportional to r. The smaller the epsilon r, the more will be the bandwidth, and the best one is the free space, because there epsilon r is equal to 1. So that is the best dielectric substrate for the antenna design. If you can use free space as substrate, that is the best one. But again, always it is not possible. There are methods of using free space as the substrate, but that is not our interest right now. So free space is the best one. Then replacement of free space is a foam. Foam is very close to a free space. Its dielectric constant is very close to free space. Therefore, you can use a foam substrate to get a high bandwidth. So a foam substrate, sufficiently thick foam substrate, but not very thick. It should be less than 0.05 lambda 0. Up to that, thickness of foam substrate will give you the best bandwidth that you can design. Then the next part is, it is directly proportional to the width W. Now, why it will be directly proportional to the width W? The larger the W, the larger the fringing field. Smaller the W, the range of fringing field is restricted to W. So if I keep on increasing W, fringing field will keep on increasing. The more the fringing field, the better is radiation. So therefore, we will get more radiation. So larger W will, so it is directly proportional to W. But problem is, if I increase W indefinitely, then again TM10 mode will not be there. TM10 will be there, then there will be other modes. Other higher order modes will keep in, because there will be variation along the width. Field variation will be there. Half wavelength field variation will be along the width if W is very large. Therefore, we cannot go for very large W. There is a constraint on W. So it is usually we take W to be less than 2L. So W has to be less than 2L. What we do is mostly we take W is equal to 1.5L. Of course, we can increase that from 1.5 to 2. Between these two values, you can take W when you are designing the microstrip antenna. So typically W is equal to 1.5. Now, what are the let us see some typical results. Generally, it will have 3% bandwidth. Microstrip antenna will have 3% bandwidth if h by lambda 0 is 0.02 on a typical substrate of permittivity 2.2. But this becomes around 10 when we use a thick foam substrate. of same amount, h by lambda 0 is equal to 0.02, but epsilon r is equal to 1. That gives you, or epsilon r is very close to 1, that gives you around 10% when a thick foam is used. There are special feeding techniques like aperture coupling that we discussed in the last class, and stacked patches. One patch above that another patch. If I take two patches stacked one over another, then effectively we are increasing the thickness of the substrate. So with those methods, we can go up to bandwidth more than 50%. So for the time being, let us see what is the effect of W here. Practically, if I design a microstrip antenna, we have designed a microstrip antenna, and we have, this is the S11 plot of the for W. Now you can see the green one is W is equal to 45 millimeter. Width of the patch is 45. Then as we change it, then we are decreasing from 45. If we are decreasing it, then the width bandwidth is increasing. Bandwidth, how do you find out bandwidth? What we do is we take a S parameter. Then on the y-axis we plot the S parameter in dB, and on the x-axis we plot the frequency. This dB value, if it is better than minus 10B, which means less than minus 10B, so minus 12, minus 15, minus 20, those are the range in which we say the antenna is radiating properly, or it is receiving the feeding energy. Whatever is fed, that is receiving. So it has to be better than minus 10. So you can see for the green one it is about 55, but it is very over a very small range of frequency. If I keep on increasing, that range increases, around 10, that range increases, but matching is not, matching becomes poorer. This is one point that I wanted to tell you. Then why this happens? For that we have to understand how the impedance behavior is there. This is only the reflection coefficient. Let us look at the impedance. The impedance is, for impedance what we do is we plot it to the impedance on this Smith chart. Now again here we are using different W. Now W is equal to 45 is a red curve that you can see, and green curve is 36, 38, etc. Now if you look at these curves, there is a circle inside the central circle, shows you VSWR is equal to 2. So within that circle VSWR will be within 2, and VSWR 2 corresponds to S11 minus 10 dB. So within that portion, within that circle, we should have the largest portion of the antenna, largest portion of the frequency. Right? That portion will give us the maximum bandwidth. If I see from the green one is mostly capacitive. It is below, near the, and upper one, orange one is mostly inductive. So what we are doing, as we go from green to the orange, we are going from capacitive to inductive. Now where it will resonate, it resonates at the point where these curves, the impedance curves, cross the resistance curve, pure resistance curve, which is the horizontal line. Now if there are two crosses, 2 points, it is crossing at 2 points, then that indicates that 2 different points without a loop, that indicates that we are exciting a higher order mode or some unuseful mode. So it should cross that once, at least once. So the lines which are above the horizontal line, there it is not radiating, there is no resonance, so those lines are rejected. Below the line there are points where it is crossing it more than once, or there are points where it is crossing it only once within the circle. So the points where it is crossing it with only one, and where the difference between the frequencies at the two edges of the unit circle, or the VSWR is equal to 2 circle is maximum, that is the curve, or that is the width that we should choose for the antenna. That gives you the maximum bandwidth. Then we'll discuss about the radiation pattern that we had already seen. We had found out expressions for radiation pattern. We have seen pictorially how the radiation. Let us have a discussion. Now, if you remember those pictures, or I'll show you the next slide. Repeat those pictures. The E-plane pattern is typically broader than the H-plane pattern. That we'll see in the next slide. The ground plane, as you know, ground plane is finite length. We cannot have an infinite ground plane. So we have a ground plane, finite ground plane. So the ground plane is truncated. Since it is finite, it is truncated. The truncated ground plane, that causes edge diffraction. At the edge of the ground plane, there will be diffraction of the field. So the fields that exist at the edge, they will be diffracted. Because of the diffraction, they will degrade the radiation pattern by introducing ripples in the forward direction in the radiation pattern and some back radiation. That comes because of the finite ground plane. Then the vertically polarized E theta and the surface wave pattern, they are angle dependent and both of them vary as cos theta. Therefore, E theta due to the antenna will be contaminated by the surface wave pattern. So we have to minimize surface wave, that we have discussed in the last class. So this distortion is more severe in the E plane because vertically polarized E theta is of the variation cos phi, like the SW pattern, surface wave pattern. Now let us see what I said. Let us see it in picture. In the picture you can see both these. Red line is for infinite substrate. So for the red curves you will see that they are smooth. There is no back radiation. Blue line is for a 1 meter ground plane in this case. Now you see the E plane pattern is wider, broader compared to the H plane pattern, or H plane pattern is more directive than the E plane pattern. That you can say. That is one point. Second is, if you look at the real pattern, which is blue, there are distortions in the blue pattern in the forward direction which is towards 0 in both the cases, but in the E plane the distortion is more marked because of surface wave, and there is radiation to the backward direction. That also you can see. So this is all that we discussed about radiation pattern. Then the directivity. Then we come to the directivity. Now directivity is not sensitive to the substrate thickness. To a large extent it is independent upon the substrate thickness. But if the substrate is very thick or very thin, then it can have some small effect. And this is higher for lower permittivity of this dielectric substrate and lower for higher permittivity of the dielectric substrate. Here you show a curve which shows the directivity versus H upon lambda substrate, normalized substrate. So you can see as we increase the substrate thickness or electrical thickness of the substrate increases, this is actually for W by L with to length ratio is 1.5. As I told you, thumb rule, we take W by L is equal to 1.5 usually. So this is for an antenna for which W by L is equal to 1.5. Now you can see there are two epsilon r. The above one, top one is epsilon r 2.2. Bottom one is epsilon r 10.8. 2.2 is almost above 10.8 for all cases, unless there is a very thick substrate. As the thickness increases, 10.8 overtakes 2.2, but otherwise mostly it is above 10. Then let us see what happens to the efficiency of the antenna. Now you can see the plots for efficiency measured in dB or calculated in dB versus frequency. Now you can see as the frequency increases, efficiency initially increases, then it either decreases or remains constant. Now you can see when width of the patch, WP indicates width of the patch. When the width of the patch is small, the efficiency is minimum, and when the width of the patch is maximum, the efficiency is maximum. This we discussed earlier. Width, increase in width means more fringing field. More fringing field means more radiation, so more efficiency. So if it goes above, if the width increases, then the efficiency will increase. For the antenna, efficiency will increase. But as you increase the frequency, after a certain range, it will start decreasing. Usually it starts decreasing, reducing. So it is region is same. Region is as you increase frequency, what will happen? Basically, the frequency is you take W by lambda. So frequency increased, lambda is decreasing, lambda decreasing. So width is electrical decreasing. So that is major reason. So width is small means efficiency will be reduced. So with this, I'll take a break of 2 minutes, 2-3 minutes. Then I'll come back to the last lecture in this series, 6th lecture, and we'll conclude microstrip antenna that is necessary for you. आठटाକୁ 4टा 2 खंड कर दे 4टा 5 ଥିଲା हाँ अयो पानी टे दे दियो पी दो तोर देले को आसाराम होई जीवो
सियोर में को पिलाने रेस्पॉन्ड करले तो शांति मेसेज तो लिखी थी रवि सर क्लास करेगा सर पर से समस्त एका साइंड आउटपुट करेंगे जब लिंक ना आसले ताले आज क्लास बंद सोमवार दिन होगा
एरर दउची ना आसुची केते पिला अछन देखलिए
3टा
ताने 4 3 17 पिला अछन बर्तमान हाँ गोटे पिला इतले मु सार दे आज आ रखिनी हाँ आ तो 4टा स्लाइड ओके टा स्लाइड देख लो
एला में 39 रहता
हाँ
39 बोलो
40